Good day, everyone. Thanks for tuning in to today's lesson. Once again, we're going to be talking about solving systems. We're going to be having a total of 3 different videos from this one particular lesson. We're going to go through each one for each day. Overall, if you notice, we should have 3 different total. We should have a graphing, elimination, and substitution. 3 different methods to actually solve a system, okay? For each of these videos, you can see me go through fairly quick. I'm going to go through a lot of different problems, a lot of different things that you can see. And then we'll also go through it in class the next day, okay? In this video here, we're going to specifically focus on graphing, how to solve a system using graphing, okay? So what we're going to do is actually jump right to the second page here with number 3. We're going to talk about a few things, and then we'll kind of get moving and actually on how to solve these out. So number 2 starts with what problems can arise when solving system equations by graphing. We're going to hold off on this problem. We're actually going to wait, okay? So we're going to come back to this one towards the end where we actually kind of discuss why is there issues with solving it this type of method. But from now, we're actually going to talk about what a system is and then how we can actually solve this out. So for A through C here, we're going to go through a couple of these and actually just talk about what's happening and what is going on with these types of graphs here. So first and foremost, if you notice, we actually have a system right here. This here is a system of equations. Simply put, it's a system of equations where in the end of the day, they're going to come up with the same value of answers at some point, okay? Both y equals x plus 1 and y equals negative x plus 4 at some point can be invoked into a system just because at some point they can also be equal to the same thing, okay? Because of that, we can basically assume that at some point we are going to have an x and a y value that's equal to the other equation's x and y value, okay? Throughout the next couple of days, we're going to be talking about ways to actually find each of those values, okay? We have 3 different total methods, and today we're actually specifically talking about how to actually solve this using graphing, okay? So simply put, to solve a graphing method, we are going to graph out both of these equations, okay? We're going to try to graph out y equals x plus 1 and y equals negative x plus 4. The key thing that we want to think about is basically everything we've talked about the last couple of weeks with our graphing techniques, dealing with y equals mx plus b is going to be applied within this problem. So let's get right into it. For this problem to actually work, we have to graph out both of these equations separately. So let's start with y equals x plus 1, okay? Key thing how I have to look at this problem is I'm trying to figure out what's my slope and what's my y-intercept. Well, in this equation, if we assume the value in front of our x is just a 1, that's going to tell me that I should have a slope equal to 1. And on top of that, the other value is always the other value next to the x is always going to be our y-intercept. So this value here is going to end up being our y-intercept. So our b value is equal to 1. That tells us where our starting point's at. So we're going to start at 1. And we have a slope of 1. So I'm going to go to my graph, and I'll detail this one in black to start. We're going to have our original point starting at 1 as shown. And then since we have a slope of 1, we're going to count up 1 over 1 each time to make our dots. From there, we can draw our line. And it looks like so. Okay. Well, we did it for one graph. Now we got to do it with the other graph. So now we have to do the same thing, but we have to graph out y equals negative x plus 4. Same process. In this case, we have a negative x to start. So our m is going to be equal to negative 1. We have a b value equal to 4, our starting point. So I'll go ahead and mark this one with the blue dot. We have a starting point at 4. And we have a slope of negative 1. So we're going down 1 over 1 each time to get a graph like so. And we can go ahead and plot that out using our nifty gadget here to get a line like so. Okay. In this case, or in this problem, we basically want to determine the number of solutions, and then on top of that, be able to figure out, is there a specific value here? Okay. But here's the key thing to understand. Specifically, if I look at this problem, I can pretty much solve out and say that this value, where they cross at, must be a solution. Okay. Where two lines cross that means at that specific spot right there, that's where these graphs must be equal to one another, correct? Okay? So I know in this part, when it's asking determine the number of solutions, I know that this graph must have one solution. Okay? Now, here's kind of the issue with this one. And this is where kind of the issue of graphing comes into play. Even though I can find out that this graph has one solution, when I look at this graph in general, let me take some of these lines away for us. When I look at this graph in general, I really don't know where that point is crossing at. I can guesstimate what coordinate this is, but I don't really know. Okay? So this is where graphing kind of comes into an issue. While it's nice to know that they cross at a specific spot, so I can assume that in somewhere in this region where x is about 1.5, y is about 2.5, at some point in that region, I'm going to have an answer. I don't really know what that exact answer is. So when it asks for problems like this, like what problems can arise when solving a system of equations by graphing, yes, we can figure out, okay, they cross at that specific spot, so we have that answer right there. Unfortunately, it comes out to this specific problem of it's hard to be exact. So it can't be exact at all times. Okay? And this is kind of the key thing with graphing. It is a nice method. Okay, it's a nice method to have and actually use. For example, if these lines cross at a very nice location where I could easily see what coordinate it passes at, then I could find the answer. But in a lot of times, it doesn't do that. It causes problems like this, where they don't cross, or in this case, where they cross at a specific spot where I can't really find the answer, you know? So we do have a solution here. Unfortunately, we can't figure out what it is. Let's go on to the next one. Letter B is y equals 5 plus 2x, y equals 2x, okay? We'll go ahead and move a little faster with this one. I'll do this top equation in red and this bottom equation in green. For the top equation, we have a starting point of 5, and we have a slope of 2. So we go up 2 over 1, and we have a graph that looks like so. Okay? In green, basically if you think about the equation in green there, the one that's next to the green line, y equals 2x doesn't really have a starting point, so we assume it's 0. And then the value next to my x is a 2, so I go up 2 over 1, up 2 over 1, up 2 over 1. And I get a graph that looks like so. Oops, let me fix that a little bit. That looks good. In this case, we run into our second problem. When I graph problems out like this, when I see this type of problem, I need to have an exact crossing point to actually get a solution. In this case, I don't get any crossing points. So when I graph this out, this actually comes out to be no solution. Okay? Because even though I'm trying to solve for x and y, because they're not crossing at any point, I can't have a solution. At no point will these two cross and give me a specific value. In this case, I just do not have an answer. Okay? So once again, we kind of run into a second problem. When we graph it out and we get values like this that have the same slope and have parallel lines that never cross, you can't have a solution for that one either. Let's talk about our next one. Y equals 2x plus 1, and then 2y equals 2 plus 4x. Same concept here is I got to be able to solve this out and graph it. Well, first off, let's simplify this bottom equation. Okay? If I divide this 2 out to both sides, it's going to cancel here. And on the other side, I'm going to be left with y equals 2 divided by 2 is 1, and then 4 divided by 2 is 2x. Well, if I rewrite that bottom equation, 2x plus 1, isn't this and this the same thing? To where if I graph it, they're going to be the same exact line, right? If I simplify the bottom one and I graph it, it's going to be the same exact line. So if I graph this out, I have a coordinate starting at 1, and I go up 2 over 1, up 2 over 1. draw my line, and I get a graph like so. But the problem is that once again, I technically graphed out two lines with only a singular graph there. Well, what's actually happening is that even though there's only one line there, these two are overlapping one another constantly. Because of that, we state that this is infinite solutions. Every single problem or every single value of x and y that line crosses has to be an answer because the graphs are always touching. They're always in the same spot, okay? So we kind of can see that in these particular problems, we have these certain solutions, but the only way to have a specific solution is when they cross at a singular location, okay? So graphing is a nice tool to have because I can get problems like 3A here where they cross at a singular point and I can kind of have an idea of where that value is going to be. But at the end of the day, this is going to be the one strategy that we rarely use simply because of this idea. I cannot be exact with these values. Okay, it's hard to be exact with a graphing value unless they cross at a very ideal location. If they don't do that, if we get decimals as answers, then it's hard for me to actually figure that out because we don't have a decimal graph. Okay? So once again, this is one way to actually solve out a system. I could graph it out and see where the location of their crossing point is. However, once again, when we do that, we run into issues. All right? Thanks for watching for today. Go ahead and finish up with the questions itself. I will be discussing this in class tomorrow, and then we'll get started with substitution and elimination with the next couple of videos. Okay? Thanks, and have a great day.